So today in this video we are going to learn about the Wheatstone bridge. So now it is written, you see that the Wheatstone bridge is an arrangement of 4 registers in the form of a bridge used for measuring one unknown register in terms of other 3 known registers. So this is known as the Wheatstone bridge. So the shape of the Wheatstone bridge will be like a bridge. Okay. Now we'll draw the exact diagram of the Wheatstone bridge so that you can understand that how it will be, how it is look like, and after that we'll explain how we can find out the unknown resistance using this setup. So see, this diagram will be look like this. This is one resistance, this is another. It looks like a kite. Okay, so this is the Wheatstone, this resistance you can give name P, this one is Q, and this one is R, this is S. So this P and Q are fixed resistance, so S will consider as unknown resistance, unknown, and this one is a variable resistance. See, this arrow determines, because we can adjust this value so that do something so that we can find out this unknown resistance. Now you have to connect battery here. So this is the wire and a battery is connected in this way. This is your EMF of the battery. And one more thing you have to connect a very sensitive galvanometer here, and this B and P point, B and D point you can write. So this one, this is your galvanometer. So G is the galvanometer, and also G is also is equal to the resistance of the galvanometer. Resistance of the galvanometer. Okay. Now see, the I current is coming from this battery. So according to junction rule, the current will be divided into 2 parts. So one will go here, that is I1, another will come to this side. So you can write this is I1 and this is I2. You can take any other things, I1, I2 also. So this I1 and I2, this I2 will go here, and it will also divide it into 2 halves. One will go in this direction, another will come to this direction. So the current which is coming to this direction will be known as Ig, and the current which is going to this direction will be known as I2 minus Ig. So remember, in this junction the current which is entering and the current which is leaving will be 0 according to the Kirchhoff's current law. Now in this case, I1 will come here and Ig will come here, so they will combine together and they will become I1 plus Ig. So I1 plus Ig current. So then this I2 minus Ig and I1 plus Ig will come here and will form what? I1 plus I2. So what is I1 plus I2? So I1 plus I2 was nothing but I. See, I was divided into 2 parts, so this is I. Okay. So again I current will come back to the battery. So this is the whole setup. So first what I have to do, you have to use the Kirchhoff law, KVL, in this loop. So you give the name ABC, and this is already. So now we'll put a loop here. This one will use another color to understand this. We'll use a loop here, and also we'll use a loop in this here. Okay. So first we'll apply the loop. So applying KVL in the loop, in the closed loop. What is the name of the loop? ABDA. See, ABDA. It's a loop. Now, what are the things we learn? We learn that this current, see, I2 is going in this direction, and my loop is also going in this direction. So, and P is the resistance here. So, you can write I2 into P and minus. Okay. And then here also, current and loop direction also, the loop is also rotating in this direction, clockwise direction. Current is also going in this direction. So, minus Ig into G. And then here current is going in this direction and loop is going on the opposite direction. So, it will be I plus I1 into R is equal to 0. So, this is my equation, and already I told you G is the resistance of the galvanometer. So, you can write this is the equation number 1. Now, we will apply the loop in this loop B, C, D, B. So, applying KVL, again applying KVL in the loop. The loop B, C, D, B. This loop. So see here same thing. I2 minus Ig is going in this direction. Loop is also going in the same direction. So minus. So minus I2 minus Ig into Q. Then again here opposite direction. Loop is opposite direction. So I1 plus Ig into S. And you can also see loop is going upward direction, current is coming downward direction, Ig is the current. So again it will be plus Ig into G will be equal to 0. So this is equation number 2. Now we got two equations, 1 and 2. Now there is one thing called balanced condition. So first I'll tell you balanced condition. Balance. What is the meaning of balanced condition? So balanced condition of the Wheatstone bridge means there will be no deflection in the galvanometer. So now how we can do that? There will be no deflection in the galvanometer. So we'll adjust this value, R value, in such a way that the potential at B and the potential at D will be same. We know already that if there is a potential difference, the current will flow. If the potentials are same, then what will happen? No current will pass through this galvanometer. So that condition is known as the balance condition. So you have to find out the condition, the balance condition for this one, and then we'll find out the relation between P, Q, R and S, so that we can find out the unknown resistance. So what I said, in the balance condition, no current will flow through the galvanometer. So no current will flow through the So what you can write from here, that Ig will become 0. Why? Because the potential at B and the potential at D will be same. So Ig is 0. Now we'll put this value Ig 0 in these two equations. So what we'll get? Putting in equation 1. We'll put in the value Ig is equal to 0 in this equation. So we'll get minus I2 into P plus I1R is equal to 0. Or what you can write, I1R is equal to I2P. So from here we will find out the ratio here. I1 minus I2 is equal to P by R. So this is one ratio we got. This is equation number 3. Okay. Now we'll put the value of Ig is equal to 0 in equation number 2. Putting Ig is equal to 0 here. Ig is equal to 0 in equation 2. What do you get? So see, minus I2 into Q, minus I2 into q lies 0, so minus I2 into q, then plus I1 into s is equal to 0 because this will become 0, so 0. Now again we can write I1 into s is equal to I2 into q. Okay, so ratio will find out I1 minus I2 is equal to q by s, equation number 4. So from these two equations, from 2 and from 3 and 4, what you can get? Compare P by Q is equal to P by R is equal to Q by S. So P by R is equal to, right, Q by S, or S is equal to or you can write P by Q is equal to R by S, whatever it is. So S is equal to, get Q by Q into R by P, or you can write P by Q. Remember, this is very common, this one. So P by Q is equal to R by S. So just reverse it, P by Q is equal to R by S. So remember this one in case of Wheatstone bridge in balance condition, that P by Q, this ratio by this ratio, is equal to this by this. So it is a very useful thing. It is used to determine the unknown resistance. So finding out the value of the resistance is very important, and in practical applications. So that is why it is used. So you can accurately find out the unknown resistance using this concept. Now we'll learn about some practical applications of the Wheatstone bridge. So now, where the normal you can use this one, or do it in this case. So here you can see this is the Metre bridge. So what is Metre bridge? Metre bridge is the practical form of Wheatstone bridge. You can write out Metre bridge. Metre bridge is a practical form of Wheatstone bridge. So it is also works on the principle of balanced Wheatstone bridge. You can write out it is also worked on the principle of balanced Wheatstone bridge. Now I'll explain you how it is related to Wheatstone bridge. So already we know this is the diagram of the Wheatstone bridge, this one. So P by Q is equal to R by S. Galvanometer is there, G. EMF is there. Now just you reverse this one. Reverse means what? You just make upside down. That means R will go to here, then S will come to here, then P will be here, and Q is here. So this one is variable, this one also become variable. So this is G, and this is your E. So just make a little bit alter this thing. Okay, now how we can implement this one in a practical use. So here is one setup. Draw it. So this is the metal stripe, made of metal. This is metal. There is one connection point is there. This is also one part of metal. This whole thing is set up on a wooden plate. So these are all conductors. These are all conductors. They're all connectors are here. Meter which you can also see in our physics lab. So this is the R. This R will come to here. This is the R. We'll use a resistance box here, which can vary. So resistance box. RB means resistance box. Here. Now we'll connect unknown resistance here. Unknown resistance, you can write S. So S will come to here. Then instead of P and Q, we'll use 1 meter long wire which is made of manganese or constantan. I tell you why they are using manganese and constantan also. So there is one scale also here attached, 1 meter scale. Exactly starting from here, this is a scale, meter scale. Meter scale, 1 meter scale is there. Now this part, a battery is connected. Okay. This is your EMF E. This part has come to here. P and Q has come to this here. Now, never I told you that is where is P and where is Q. So see, in this case, a galvanometer will be connected to here. These are galvanometer, and a jockey will be connected. It's a movable wire. Okay, this is called the jockey. Jockey means which can change. That is called jockey. So this can change. What it can change? It can change the length. Okay. So it's called jockey. So now this will become your P. This part from here to here will become P, and from the remaining part this will become your Q. Okay. So you can give the name A and B. So first what we'll do, working of this Wheatstone bridge. So first we'll connect one unknown resistance here. It will connect a unknown resistance S. And we'll fix one known value of resistance box here. Then we'll switch on, there is one switch will be here. We switch on this one, the setup, and we'll start to find out. We'll take this jockey from here, then with that wire we'll start to pull this one jockey in this way, like this way. And then according to the movement of the jockey, we'll see the deflection in the galvanometer. So now one point we'll find in this wire where the galvanometer will look like this. Galvanometer having one needle here. This type of 0, and this side is 30 division, this side also 30 division. Okay, so this is set up, and the plus and minus is there for the galvanometer. It will look like this galvanometer. Now at a particular point we'll find that this hand will come to 0, and then if we go beyond this one, then this hand will go to that side. Now whatever we have to fix it in 0 position. We'll just find out, and then we'll mark it this point. And then find out this length. Suppose this length may be L. This length is L. Take this length is L. Okay. Then what is the remaining length? Remaining length is already 1 meter. 1 meter means 100 centimeter. So 100 minus L. The remaining length is 100 minus L. Okay. Now in this wire, say lambda is equal to resistance per unit length. This is wire. So for L length, what is the resistance? P is equal to how much? P is equal to how much? Lambda into L, this is the resistance. And what is Q? Q is equal to 100 minus L into lambda. Okay, because lambda is the resistance per unit length for this wire. This wire is made of manganese and constantan. Why? Because this wire is having a constant resistance, uniform resistance. So when they connect the current, the current will pass through this resistance. You know, if the current passes, as it is having resistance, the temperature of the wire will increase. But as it is manganese, made of manganese and constantan, so temperature coefficient of this wire is less. So that is why you are using this type of wire, manganese and constantan. Now see what we got for P. P is equal to lambda into L, and Q is equal to 100 minus L into lambda for some value of R. Okay, what we'll do now, the Wheatstone bridge is now in balanced condition, because in this point we found the deflection is 0. That's called null deflection. Okay, null deflection. So we can use the formula called P by Q is equal to R by S. So we'll use this formula. So P is what? Lambda by L. Q is what? 100 minus L into lambda, and then R is R here, because already known value. You can see the value from the resistance box itself, and the S is unknown. Then see, lambda will get cancelled. You have to find out S. So S is equal to 100 minus L into R by L. Okay, so this is your formula. You can find out the L also, and you know the value of the R, and you can find out the value of the unknown resistance. So like this way, the Wheatstone bridge is used to find out the value of the unknown resistance. Okay, so now in this case, if the value of the R is nearly equal to 0, nearly equal to S, if R value and S value are both the same, so definitely you will find out the null deflection exactly in the middle position. Okay, so thank you very much. So next class we'll continue with some numericals or some other things. Okay.